Teleportation is a common VR locomotion technique which supports discrete movements of the user without requiring the user to move physically, hence lifting the play area restrictions. To teleport, the user first selects a target position and his virtual viewpoint will be instantly transferred there. We argue that while previous teleportation methods always ask users to manually select destinations, it could be challenging for users to choose ideal target positions in a virtual environment. To address the issue, we propose a scene perception-based VR teleportation approach that automatically searches for desirable positions in the virtual scene, and suggests them using teleport anchors to users, which are presented as cyan glowing columns in the video. Here is an overview of our approach comprising a scene perception prediction stage, and a teleport graph optimization stage. In the scene perception prediction stage, our approach first samples positions densely in the free space, and synthesizes a panoramic image at each position. Scene perception graphs are extracted from the panoramic RGBD images based on object detection results, and are passed to a GCN-based prediction model to generate their corresponding scene perception scores to build a score map. These scores indicate the desirability or human preferences of their corresponding positions. In the optimization stage, we encode a few considerations into a cost function. Here shows the importance of such considerations by omitting each cost term in the synthesis. With the SP score consideration, positions with high SP scores are sampled. With the connectivity consideration, connected graphs are synthesized, thus users can traverse the whole scene continuously. With the area coverage consideration, areas highlighted in red are covered. With the room coverage consideration, the bathroom at the lower left is covered. With the redundant coverage consideration, overlap of neighborhood areas of the highlighted nodes decreases. Here is an example of teleport graph optimization procedure. In a teleport graph, nodes encode the selected positions and edges encode visibility between nodes. We formulate our approach as an optimization problem to search for an ideal teleport graph. We show some synthesized teleport graphs and example views at some anchor positions. We extend our approach in a few experiments to examine its generalizability. For example, users can control the density of teleport graphs. Here we show a synthesized sparse teleport graph. And here is a dense graph. This feature would be useful when some users may prefer to traverse a scene quickly by visiting key positions only, while others may prefer to visit more positions. Our approach supports recomputation of the teleport graph to cope with layout change. Based on an initial graph, if we move the table to the right, our approach fine-tunes the initial graph to produce a new teleport graph. This feature would be useful in some interactive VR applications. We allow users to replace the SP score prediction model with specific criteria and apply our approach in other environments. For example, to facilitate wayfinding in this natural park scene, we define the SP score of a teleport position based on the visibility of a flag within a certain distance, and present a synthesized teleport graph. The color of a node denotes which flag is visible from that position, and a majority of positions on this graph have a visible flag in their proximity. We conducted a user study consisting of 2 tasks. In the navigation task, we compare our method with the conventional point and teleport approach that requires users to manually determine teleport positions. Our method improves the navigation efficacy. To reach the same exploration ratio of scenes, participants generally performed a fewer number of teleports using our method compared to the point and teleport method. Here shows the trajectories of 2 participants. The participant using point and teleport performs many intermediate teleports along his trajectory. In contrast, the other participant aided by our teleport graph traverses the scene more efficaciously. He often chooses the anchor positions as destinations. He also spends more time perceiving the interesting regions. In the desirability evaluation task, which was conducted in a two-alternative forced choice manner, participants chose more desirable views at either anchor positions or positions they manually chose in the navigation task, based on the surrounding objects. The results show that generally, more participants prefer to choose positions suggested by our approach than their manual choices, which suggests that our scene perception prediction model is capable of predicting desirable positions. Please refer to the paper for detailed analysis. This is the end of our video. Thank you for watching.